An object is moving along a straight line with a position function s of t, where s is in meters, t is in seconds, and t is between 0 and 10 not included. The graph below represents v of t, the object's velocity function. So when you're looking at pictures involving graphs that you have to read and answer questions about, the very first question you need to ask is, what am I looking at? And here clearly it states we're looking at velocity, but more importantly, what does that mean in terms of derivatives? Am I looking at a function, its first derivative, its second derivative? So we want to measure position, which is s of t, and we know that velocity is actually s prime of t. So we are actually looking at a derivative graph because that's going to completely change how we read what's going on in the function. The other thing that you want to make sure you verify is, what is the domain of this function? This particular graph, it was called out. We can see that we have nice big open circles at the edge, but you always want to verify, is that graph running off the edge? Are these things really going to infinity or not? So I find it to be a good rule of thumb to explicitly write the domain of the function you're looking at. So that way we know any answers we get outside of this are not acceptable and we've gone too far. Part A says, determine the intervals in which the position function is increasing. So a function is increasing when its derivative is positive. So that means if we're reading the derivative graph, we only want to look for the areas where the derivative is above the x-axis. Those are the positive values. So if we look at our function, we can see it's above the x-axis from 0 to 4. And it's also above the x-axis from 8 to 10. You'll notice on the written key, it will also accept values with closed intervals here. Technically, those are not correct. We're just a little bit forgiving if you include those values. But since the function doesn't even exist at 0 and 10, it doesn't make any sense to close those intervals. Also at 4 and 8, the derivative is 0. So without knowing a little bit more about what's happening on the original graph, usually we don't say something is increasing or decreasing, but it is possible that 4 and 8 could be inflection points, so that's why we're a little bit lenient on those brackets. Determine the interval in which the graph of the object's position is concave upward. So we know something's concave upward when the second derivative is positive. So if you are looking at the slope, or excuse me, at the first derivative graph, the only way to get a read on the second derivative is to look at the slope of the tangent line. So we need to know, where is the slope of v of t positive? So if we go back and look at this graph, if we imagine a tangent line for this graph, we can see that it's got a positive slope. Here it's 0. Then it becomes negative. It stays negative until it goes to 0 again. Then it becomes positive, becomes 0 up here, and then negative again. So that's what we mean by looking at the slope of this graph. So there is a positive slope. That's where the second derivative would be positive, is going to be from 0 to 2. At 2, it's 0. It goes negative again all the way down to 6. And then from 6 to 9, it becomes positive again. It says determine the values at which the position function has a relative minimum. So we know that a relative minimum occurs whenever s of t goes from increasing to decreasing, or excuse me, decreasing to increasing. So we want to look for where v of t, which would be the derivative of this, changes from negative to positive, so that the original function is decreasing and then increasing. So we want to know where it goes from negative to positive. So if we look up here, here's where the graph goes from positive to negative. That would be a relative maximum. But here's where it goes from negative to positive. That would be a relative min. So the only value, oops, is at t equals 8.